Non-permissible values occur when we have restrictions in functions, and typically they're by dividing by zero or by or restrictions on the function. So example, dividing by zero is this first one here. So I cannot divide by that zero. So I have to make sure that I have a restriction here that x is not equal to 2. If x is equal to 2, I'm dividing by 0. Once I've established that restriction, I can actually now simplify this. And in this case, there is a common factor of x minus 2. If I factor out, so if I factor that out, and I'm going to factor out a negative out of here and make that x minus 2. So if I factor the negative out, it will switch those around, and then I can now cancel this. Because I've stated restrictions, I can now cancel this out. I end up with y is equal to negative 2x. So when I graph this, these two graphs, negative 2x and this x squared minus 4x over 2 minus x, they are exactly the same graph. However, this has a restriction at x equals 2, and this restriction will show up as a hole in this graph. Looking at B, there are restrictions on dividing by 0. So the tan has a divide by 0 restriction. We also have a square root, which has a domain restriction. And we also have to worry about that square root being equal to 0. So I'm going to first start off with that tan restriction. Well, tan really is sine over cos. Okay, so if it's sine over cos, then we have to worry about the cosine being 0. The cosine is the horizontal, so we cannot let the horizontal equal 0. We cannot have those two positions on the circle, otherwise tan is undefined. So that means then that x cannot equal pi over 2, 3 pi over 2, and all the repetitions of those. And we can simplify that into x is equal to pi over 2 plus n pi, because the restrictions repeat themselves every 180 degrees, or pi. Then we move on to the denominator restriction. Well, the denominator restriction can't be equal to 0, so x can't be equal to 3. However, x must also be positive. So that means that x must be bigger than 3. It should be bigger than or equal to 3 for the square root, but it cannot equal 3 because that means I'll divide by 0. So this restriction is based on the restriction of the square root function not being able to square root negative numbers. When I take a look at this one, we have 3 different restrictions that we have to consider. The cosecant has a divide in here, so we have to worry about that sign being 0. The tan has a divide, which means that the divide in the tan, or the cosine like we have up here, can't be equal to 0. And also the denominator 1 minus tan can't be equal to 0. So I'm going to start off with the cosecant. Cosecant is 1 over sine, and I can't have sine being 0. Sine is vertical, so sine is 0 in those two positions. That means then that the x value, the angle, cannot be equal to 0, pi, 2 pi, dot, 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 and it goes in both directions. So we're going to summarize that as n pi. Okay, so every 180 degrees starting at 0, we cannot have angles that hit those points. Okay, pi, 2 pi, 3 pi, 4 pi, etc. When I take a look at my tan restriction, I just go back up to this green circle. Tan is going to have cosine in the denominator. I can't have the cosine hit those values in those red dots. That means that I'm going to have the same restrictions I had before. So from the tan, x cannot be equal to pi over 2 plus n pi. Okay, and n is an integer like before. And then lastly, the denominator cannot equal to 0. So I end up with tan x not equal to 1. Well, tan is slope. That means then that it cannot hit these 45-degree points. So x cannot equal pi over 4, 3 pi over 4, and we're going to repeat these solutions every half circle, so it's going to be n pi. And where n in all three cases is going to be an integer. For D, we have the cotan. Okay, the numerator is usually not a problem, but the cotan has a divide. It has a divide by sign. So we're going to have the same restriction here as we did here. Okay, so we can double up on that. We also have a domain restriction on log, that x must be bigger than 0, but we also have a domain restriction on the square root. That log value, whatever we get out of that log, must be bigger than 0. Okay? It can't be equal to 0 because, again, since it's in the denominator, it has that added restriction of divide by 0. So how do we deal with this? Well, first of all, let's make sure we understand what the log function looks like. All log functions look like this, okay, regardless of the base. And I want that log to be bigger than 0. That means it can't equal 1. That x value cannot be equal to 1, because if x is 1, log base 2 of 1 is equal to 0. I'm dividing by 0. It also has to be positive, so I need all the values that are positive or to the right of 1. Okay, everything on this side is above 0. That answer, that log, can then be square rooted. So that means then that when I, just going back to this picture here, the restriction, I'm going to start with I'll start with the denominator restriction. The denominator restriction then becomes x must be greater than 1. Okay, any x is greater than 1 will avoid the 0, and it will also give me positive log values, which then I can square root. So that's the restriction from the denominator. In the numerator, the cotan restriction was the same as sine. So if I take a look at my sine, it's in these two positions here. Okay, so sine, the cotan is restricted by saying that x cannot equal 0, pi, 2 pi, or n pi, where n is my integer value. Okay, so I have my divide by 0 restrictions. I have my log restriction and square root restrictions, which helps if I understand what the log looks like to make sure I avoid the negative parts of this log. So this negative part of log I can't use. That's why I have to be bigger than 1.